Okay, well, it looks like we've got quite a turnout, and that's fantastic. So I just wanted to introduce myself. My name is John Shepard. I'm a professor here at the University of Hawaii Cancer Center. And with Peter Sadowski, I co-lead the Artificial Intelligence Precision Health Institute. Margareta Colangelo is on our call as well, and she's one of our scientific advisors. We have a speaker of the day I'll introduce in just a moment, but I also want to mention that this is a speaker series that we've just initiated, and we have quite a list of exciting speakers for with the kickoff here with Bardia, but also Adam Yala, which is an AI expert at UC Berkeley, was formerly at MIT and just joined Berkeley. Alex Stokes at the medical school here in Hawaii. Harry Trivedi from Emory University leads an AI group there in medical imaging. And Vignesh Arasu at Kaiser wow, KP. And he is also doing extensive, he's a radiologist doing extensive AI in breast cancer detection. So we've got a great lineup. The times for our talks are, scheduled to be this time. It's right at lunchtime for the Pacific, and in the late afternoon, maybe when you're closing things up on the East Coast, and for us here in Hawaii in the morning. So I hope the time works out well for everybody. Just a quick introduction to our institute. We are here to promote the use of artificial intelligence in cancer and medical research. We provide guidance to students and also resources for either faculty or our students to do AI modeling and learn the art of AI for this topic. We also have extensive data resources, which includes the Hawaii Pacific Island Mammography Registry, which has over 45 million DICOM images in breast imaging to be used as training and model building using data from Hawaii. So if anyone's interested in working with us on AI topics, we are open for business and love to collaborate. Peter, did you have anything to add to that?
Oh, that covers it.
Okay, great. So let's just move into our talk. Our first speaker is Bardia Konh. He's at University of Hawaii here, and my notes are covering the page. My slide is covering my page of my intro. Sorry, Bardia, but I'll let you introduce yourself. You've got quite an interesting background that extends back to your time at the University of Technology. So maybe you could just do a quick introduction of yourself, and then we'll get started. We'll leave about the last 10 to 15 minutes open for questions. Okay.
Sounds good. Thanks much. Okay, so let me see if this slide share works. Do you see the slides?
We're seeing your speaker notes. So if you go to the top and just do a switch displays, I think we'll be okay. So it says display settings. I think if you just say switch.
Yeah, I don't see a switch button.
Display settings above your speaker presentation, on your speaker presentation view. There you go. I think if you click on that. Okay, it switched to the another screen. I thought that's where your slides would be. Go ahead and reshare and just be careful which, yeah.
You can see now?
You can see a flowing water. Is that what we should see?
Not really. How about we go like this?
That should be fine.
Okay. So yeah, thanks for having me. So I got my PhD from Temple University, got here at UH as an assistant prof. And we are working on medical robotics and so hardware, software control, and we are recently moving to apply some AI for prostate cancer treatments. Some of it we can see hopefully on the slide. So here we majority of talk will be on prostate cancer. That there are other treatments that we are trying to explore, but we keep with prostate cancer. So as a little introduction, we are all familiar with robotic assisted surgeries. These are 3 examples, like ear, nose, throat surgery. As you can see, there are small tubes going through the skull, through nasal. Maybe they're doing sinus surgeries, other things. The things that are important, the tools should be very small, dexterous, controllable. Also, the imaging and vision is playing an important role. So laparoscopy is the same way. It is hand-eye coordination. They see on a monitor, they have to manipulate. In knee implant, also everything, a lot of things are mechanical, so it's drilling, putting the screw, other things. So when we talk to doctors, 2 things are important. One is the tool should be dexterous, precision matters in a lot of applications, and also imaging to see where the tools are. So our group majorly involved with minimally invasive surgeries, so they should go inside the patient, do the things, the procedure most of the time, do the test, minimally invasive, less trauma, faster recovery, all of that. So what we are seeing in prostate cancer, first there are diagnoses. So we have made a couple of robots that we're going to see through this talk for prostate biopsy. The treatment involves brachytherapy. We have worked on low dose rate brachytherapy and high dose rate brachytherapy. Each of them needs a treatment plan, and the physician to tell us how much of radiation should go inside the patient, inside the prostate to kill cancer. They are divided in permanent placement of the seed or temporary. In this talk, we're going to see mostly high dose. So we need the needles to be accurately inside the prostate. There are some challenges, tissue moves, especially with prostate is very movable organ. So movement is an issue for needle placement. There are sometimes other organs in front that should not be punctured. And we need radiation to go only to prostate, not the neighbor organs or healthy tissue. What we are doing in the lab is to make a needle that can bend so that we can actively control it. Some robotic hardware, software control to manipulate it and see it. So we have done some work on imaging part, and we are going to see the work that we started recently to make the treatment plan being planned in a smarter way using AI. Good. So this is the active needle that we have made. So the tube, it should host radiation, so it should be hollow. So there are tendons inside. The tube is slotted to make it more flexible. The tendons are pulled by the motors and actuation control system to make the desired bending that we want. We have tested in phantoms to see wherever it goes, it's going to be helpful. If it's going like in front of a straight shot, then it can bend, move to the target that we want. So we can do it autonomous, so the robot decides where it goes based on the imaging. We can make it teleoperatively, give the surgeon control, those sort of things. So one other project that we have run was this handheld controller. So we made everything compact. The needle sets here, the manipulation system, which are 2 motors bending the pulling the tendon, bending the needle sits here, and then there's a joystick button. So the surgeon can bring it in the hand and manipulate. So this is work of one of our undergrad research that made this case everything be in a small size, compact to be holding. We made one other interesting needle, which is 3D printed. So there are rigid 3D printed parts, flexible parts. And the interesting thing about this needle is that these are shape memory alloy wires. When you heat them, they shrink, make actuation. So we're using that as an active actuators in the system. The other thing good about them is that we can sense how smaller they are at every point in real time. So we are trying to use shape memory alloys as sensors as well as the actuators. So it is a lot of material science involved. We need SMA characteristics, material model, hyperelastic material model of the joints that are soft parts, and also kinematics whole thing. But if we have all of these, we can say where the needle is at every point. So we don't actually need to have it extra sensors or imaging on top of the needle. We can trust the sensing capability of actuators to see where the needle is in real time. So a lot of these things are inside the body. We don't have transparent phantom like in this book to see where the movement is. Sensing, shape sensing, and other type of sensors that they attach to devices like the laparoscopy device surgery. So this was this work. Everything that we have, we made a portable robot like this. So the needle sits here. There are linear stages that moves the needle inside for insertion in axial direction. There is an ultrasound device that sits here. This is a transrectal ultrasound. This is made basically for prostate brachytherapy, but it can be used for prostate biopsy as well. So we get imaging from the ultrasound, movement of the needle, and our actuating system is sitting here, so it can also pull the tendon and move the needle left and right. We have a good imaging and image processing here that I'm going to show in a couple of next slides in order to see how that works. But everything can be automated, everything can be also teleoperated. So in this work, we are showing that we can attach two maxillary motors, and they're attached to two tendons, left and right. And then we can have this system as a slave, and the master device here is a simple joystick, and we can bend the needle iteratively, whatever angle we want in order to reach the target points that are inside the process. So this needle is made to give bending that it is needed for the range of motion that we need inside the prostate. So this work shows that was we were able to do this experiment in air. So this other work shows our capability to sense the force of the needle insertion, which is a very important measure in needle insertion, because it shows us how stiff the phantom or the tissue is based on the progression of cancer. So we would know how much of stiffer tissue we're dealing with, so that we can decide on the bending forces or insertion forces to target points inside us. So we will attach the sensor at the back of the needle while it's moving in. We can see what the force profile look like, and based on that, inform our control strategy in order to go to the position that we need. So this is very active area of research in order to see where the needle is, where it has to go. So it is very iterative closed loop control of the needle to be able to place it wherever we want, because surgeons go move it by hand and everything moves, everything active dynamic. So it is not the place that we initially like the needle to go. This video shows our way of tracking the needle tip. So we need to know where the tip is at every time. So we are using ultrasound images. It is 2D images. We are only seeing the cross-section of the needle. The point is that we have to move the ultrasound on top of the needle at all time. So we wrote scripts in order to manipulate the speed of the needle, slower, faster when the needle tip is lost or is visible. There is some image processing involved, which are pretty basic, but we can recognize the needle tip, the cross section, and then we wrote this algorithm in order to speed up or slow down the probe in order to catch up with the needle tip in real time. So as you can see, there are some spots that the needle tip is lost. But overall, we can see the shape of the needle is curving inside the tissue. Is with the agreement with the vision-based and ultrasound tracking. The other method that we have used in order to improve was to get information during the process, during the injection process, in order to predict the shape of it. So if we agree that the needle is continuum, it is smooth, and we get a nice curvature, then we can get information from 3 ultrasound slices, the position and magic curve in order to see where the needle tends to go. By using that information, that predictive algorithm, we can fill in the lost information. And that's very, very important for your control. So if you have closed loop, you don't need any points that is lost. It would be very bad for your end goal. Okay, so that was that. The other work that we have worked on was a biopsy needle. So this needle can bend. This one we have a slits towards 3 direction, 120-degree apart. So it can bend in 3 directions. This other needle that we have made is bi-directional, so it is 1 degree freedom, theta left and right. As you can see, when the needle bends, the extraction tray can open and close in order to trap the tissue. We have also did a test in phantom mirror to see if we can trap some tissue. So that is possible. It's pretty important for prostate biopsy. So prostate biopsy, they need a very typical way. They need a 12-core biopsy sample from 12 zones of the prostate to examine the whole volume of the prostate. So if they can move the needle to get tissue that they want, is very helpful. Additional to that, when they introduce the needle itself through the skin, everything moves, so manipulation helps. So here are 2 methods that they are doing prostate biopsy. On the left, we see MRI ultrasound fusion. So they take an MRI picture of the patient beforehand so that they know where the prostate is, how large it is, the contouring and everything. And then they fuse it on the ultrasound. So when the practitioner is doing biopsy on the ultrasound live, that they can see the contours of prostate nicely drawn, so they see the volume, and they can see where the possible tumor are in order to take samples from those locations. So these mark up the suspicious tissue are done beforehand under MRI, so they know where the tumor is. They fuse it on the ultrasound, and then they can guide the needle, see the needle, and extract the tissue. So this on the left, using Euronav system is one of them, is a very typical way that people are doing prostate biopsy. We interviewed a very large number of institutes throughout the US, and it sounds that like 90% are doing this method. It's faster. There is a technology, so this device is like recently introduced to market, so they like this method a lot. But this method of MRI guided biopsy, which are done in few institutes around the nation, or they do it if it is very necessary for the patient. It is guided by by the robot inside MRI, they can see a very nice image of the tumor, of the organ. If they use multiparametric MRI, they can see like this shiny dots of showing the tumor. The thing that they need to add to the MRI board is that this robot that works as a master, as a slave, in order to manipulate the needle, and they can teleoperate it from the screening room. So this is additional. It adds to the cost and of everything, like operation room, MRI for the surgeon and all of that. So they prefer not to do it, but it is very, very accurate and amazing technique. So in the institute that people are more comfortable with MRI or is available, they tend to do it because of the advantages. So knowing that, we are building our robots that can work inside MRI. Everything is MRI compatible. So the actuator sensors that we have, we chose it, the one that is MRI safe. It can move the needle forward, the robot, and backward, and then bend the needle. So there are actuators, this time piezo motors in order to be MRI compatible, to bend it left or right, and the whole stage to move up and down, left or right, in order to choose the initial position. So this will be the master inside MRI board, and then we can have a teleoperative master device like a simple joystick or this one that is half. So this is our current progress. We are assembling this system. Hopefully, should be able to test it soon. The other studies that we ran was the tissue movement. So we know that the needle goes in, everything moves. We need to have a measure of that. So we did testing and analysis under MRI in order to see where the tissue moves. Based on that, we can do better planning. The other study was a model to predict things inside tissue. So we know what kind of energy it is involved here. We can make energy-based model to predict where it goes. Using this prediction, we can loop it in our control, closed-loop model-based control in order to move the needle very far, where it needs to be. Okay, so with this background, let's talk a little bit about planning. So this is where we recently like to apply AI to have a better plan. So for example, for high dose rate brachytherapy, how it is done now, patient goes in, there will be initial scan. It can be ultrasound scan or CT MRI, counter the prostate, how it looks, patient specific, that there will be a dose planning algorithm that they know, like, okay, this much of radiation needs to go these many sources. So the source position and source time, which called the dual position and time, are important, being planned in this state. And then patient goes to the surgery room, that the needle being introduced, but then the physician said that, okay, this is not the plan that we wanted, but this is the best I could do. So what is done next is that they take another scan and then another replanning based on the actual needles that are inside the prostate. So to this time, a good plan. The radiation sources are being introduced using this machine after a loader. Radiation temporary killed the cancer patient out. So this is how they're doing it now. But we were thinking that, okay, our needle can bend, so it's more conformal to the anatomy, which is the prostate, the curvatures and everything that is inside prostate. Most of the cancer are in peripheral zone. So it is better in that term. We can plan it better. There will be less number of needles involved. We were trying to replace the straight needles with bent needles, and then see how that planning goes. So right now, with our medical collaborators, there are 3 companies that are making the treatment plans. There are one from Siemens, Elekta, and MIM. So we are writing our own code in order to plan on all of that. We take the ultrasound or CT scan images in order to find the anatomy, use medical physics equations in order to find it. So we start with cancer archive. We get some CT scans of the organs that are involved, so prostate, rectum, bladder, and urethra. The target is on prostate, so we need prostate to be hot, meaning that a lot of radiation to the prostate, not a lot of radiation to the healthy organ. Bladder, rectum, urethra should get less dosage. So we can draw the contours on these, import them in MATLAB, build our environments. We can have a 3D representations of the organs that are involved. Next step is to check on the dosimetry to see how much dosage is being introduced by the source at the distance from the source. And then we have to write the corollary to see which of these volumes, how much dosage they are receiving. So then we tried that in some of the prostate and patient that we examine this method. We see that the number of needles are drastically lower. We are still working on that. So we have to analyze the number of source, number of patient, number of data in order to see how well this method could be. It's still ongoing. We are checking the physician's data in order to make sure that these parameters to make sure that it's a good plan. Talking with medical physicists in order to see if it is good. For this one, we are using linear programming to find the ultimate optimal source and also the time, the dwell time that we. Then if we decide on the time and the position, the next thing that we like to do is to make the plan a little bit smarter. So we are trying to use reinforcement learning in order to say, okay, this is the optimal plan, so use this. So what we do is the scan, we have the environment we can build. And then in the environment, reinforcement learning, we want to say that, okay, the needle can move. So left and right, the needle moves. And then when you move the needle, you can also, on top of that, move the dual position agents. So the dual position can also be anywhere on the needle channel that is inside the prostate. So you can move deeper inside the prostate or shallower. And also we can play around with the dwell time. So how long you want this source to be active. So then we build this environment, everything moves, parameter changes in order to see if the reward is made. So the reward, we have all of those parameters that they like to have in a good plan, such as V100, V50, which is how hot the prostate is, 100% of prostate, how hot it is. And it should be based on what the physician prescribed. And we don't want it super hot, so not more than 150% of the prescribed risk. So based on that, we can see like if it is a good plan, if it's a bad plan. At some point, we have to train a neural network in order to be able to tell if it is a good plan or not. So we have to have access to a lot of data. Basically, if we have access to the software that physicians are using, we can run a plan for a patient and say that, okay, if it is good, thumbs up, like a reward of 1, or if not, 0, so that it can decide automatically. But all of these will give us an optimal needle configuration. So you say that, okay, these are the needles, these are as much as bends that each needle has to have, and these are the position sources, dual position, and also dual time in order to have a good plan. So keep in mind that if the needle being inserted by the physician somewhere that is not, that was not based on the initial plan, there should be a round of replanning, so based on the actual needle. So all of that combined, we are working deep view network reinforcement learning here is connected to the linear program So this one moves everything around inside prostate, dual position in time and needle position, and also connected to this linear programmer to give us the optimum dwell time. Goes in loop in order to see which one is rewarding, and they get the action based on that. And hopefully get us some needle position as optimal, useful, as a valid plan that can be used in practice. So this is pretty much ongoing. We are working on the code and everything. There are a lot of things that we are still debugging and trying to solve. So we appreciate feedback and everything from you guys. So we have few people, a few opening. If anyone is interested, we really appreciate your help or feedback or input in this work. So I'm going to stop in this this time, but anything that you would like to discuss further or questions, I'll be here.
That's great, Bardia. Thank you very much for that. We have plenty of time for questions, and you can either raise your hand and I'll call on you, or virtually, of course, and or you can post your question in the chat, and I can read it as well. Either way. So I'll just start with a question. Is that this is really meant for high dose seeds, right? And instead of long-term placement. So what's the overall anticipated average treatment time that someone would be have all the needles in them?
So that really depends on the plan, but the dwell time is can be like 5 seconds to 2 minutes something, but they do the seeds are attached to a wire, they insert it, and then radiation take it out, go to the next position. I think the average is 20 minutes, 30 minutes, but while radiation is inside. But before that, they put the needle inside, and then they have to take the scan. It can be ultrasound if it is not super sensitive or it's not a lot of deviation from pre-quantum. So that's quick, but then the radiation goes. I think the average is 30 minutes top, 45 minutes.
Okay. Other questions? Tim, did I see you raise your hand? I'm not sure if you have a question or not.
Did you make additive parts? With which additive parts?
Say again?
You can see in the chat some Tim is asking the 3D.
Oh, yes.
Yeah. So we had a needle that was 3D printed, that was built and tested, but the handheld controller, we have a 3D printed and assembled. So which one was it? So this has a lot of 3D printed parts. So this is assembled. We are at the stage for testing it. The other part, this was basically that they assembled it yesterday. That the number of parts are printed, being assembled. We have ordered all the motors. So this is ongoing. A lot of things are being assembled as of now. So hopefully we can run some tests soon. The flexible parts, you mean the 3D printed needle? I think you mean that. So this has these parts that are flexible. So we did 3D print these parts as well. As you can see, there are hosts to host the actuators inside the printed one, and it's very, very small. So both 3D printed, rigid and flexible. We didn't do at our mechanical engineering department. We ordered it from external printers to do that for us.
I missed a little bit about the planning stage and your reinforced learning. It sounded like the reinforced learning was going to be with regards to each time you run the procedure, you were going to compare the anticipated locations, planned locations versus the actual, and then you were going to make adjustments in your in the actuation so that you would have correct motion in the future. Can you explain a little bit more about that?
Yes, sure. So this is general way that they are doing right now using the software that are available here. So it is one planning beforehand based on the scan, and one planning after the needles are inserted. So the reason that they're doing a round of replanning is that when they insert the needle, it is not the place that they initially wanted the needle to be. So inaccurate needle placement. And they say that, okay, well, whatever it is, these are the needles that we have. So then let's do another replanning based on the actual needle. This time the needle is already in, we know where it is. So we are working on this part, only the dose planning machine that the software that is using here.
Mm-hmm.
So in here it is offline. So everything is based on reinforcement. So we are trying a number of configurations in this environment. So we virtually say that, okay, the needle moves, bending moves, dual time and dual position moves. And which one of these, if we imagine that these movements are, which one is more optimal? So we are trying to reward that in order to come to the end goal of another very optimal good plan. So while this is built, then we replace this with the in here. So this sits here. So every time that we say that, okay, plan for us, it goes to the machine that is already trained, and it gives you an optimal plan. We are hoping it works this way, but we have to make it run really fast. It takes, even for the software that they have right now, it takes a bit of time, but we have to make it like as optimal to give us like a plan immediately that they can play.
Mm-hmm. I must admit, when I was first heard about your work, I was thinking that it was a single needle going in and doing its job instead of and getting away from the multiple needles. But the curvature part of your planning, like you said, the advantage is that you can follow a nonlinear path and maybe be more efficient at having the seed travel through the prostate instead of following a linear path. So it seems like once the needle's in place, you don't move it again, right? Then everything is seed work after that. And so, and do you ever like is it part of the plan to where if the needle doesn't go exactly where you want it, you extract it and reinsert it?
Yeah, that happens. Like they can put a needle in and it's not even inside prostate, so they have to retract it and insert again. So that's one thing, and it is a very higher issue in low dose rates when the radiation source is inserted permanently. So if there are like misplacement, the seed is there permanently, is damaging other healthy organs. So it is a very, very big issue. For high dose rate, because there are several needles and they get a scan, so they exactly see it. It's less of an issue, but it's always like needle insertion is very difficult. So it is as much a higher issue is that low dose rate brachytherapy has gone like very successful, but because it is hard to place the needles, then they go to do all of these more complicated ways of high dose rates, but at least they get over complication of needle injection. So it is always a challenge.
So there's a question about that mentions the word Swiss cheese, and I think that what implied there is that when if you have enough linear pathways, then you can contour pretty efficiently, but it may require lots of needles and lots of insertions. the way I understand the curvature, the advantage is that you would actually use less needles because you're taking advantage of or less needle insertions, taking advantage of the nonlinear pathway. Does that kind of sum up?
Yeah, that's exactly what you outlined. So it is curve of the prostate curvature based on the patient, so we can plan it patient specific, and also there is urethra inside the prostate that we have to avoid, so say we can move away from that as well.
And there was also a question about nerve path avoidance. How is that taken into account with regards to the imaging or the movement of the needle?
So if they go transperineal, which like high dose rate brachytherapy goes like that, there's not much of nerves, but they try to numb the place, so it's a bit painful, but not as much. The very main issue is the placement accuracy, and if there is pubic arc interface, that they have to move the needle up and down or manipulate it to avoid that. But if we are doing robotically bendable and everything, we can have a trajectory, and there are a lot of groups who are working on path planning. So when the needle goes and it's not where we want it to go, then the path will adjust based on the movement of the targets to go. And they can also avoid the nerve path. So you can draw your path based on like whatever obstacles you have. So it's another field of research that they iteratively may make updates, adaptive path planning, they call it.
So quite a few students on the line. Any students have any questions for Bardia? I'll keep going while we wait on other questions. At one point there was excitement around cryogenic freezing instead of using radiation, and using needles to do contour, basically cryoablation. Is that a topic of discussion, or did that ever make it to clinical practice? Is that a competing technology to yours?
I think that's another method that I briefly looked at, but majority are doing brachytherapy. So I have mostly looked into that, but that's definitely another method that based on the progress of cancer or whatever it is, that they may also do that.
And there was some work with beta particles as well, I think, for a time being, but this is all gamma. Is that right? The radiation source?
Radium. Yeah, I think gamma.
Yeah. There's I think with beta you have an average absorption that is deeper than the insertion, or the maximum dose is deeper than the point of insertion. So with gamma, you have most of it's an exponential drop off from the surface. So it's just a little bit different profiling.
It is, yeah. The medical physics behind it, I agree. Yes.
It gets complicated quick on the dose profiling with different types of sources and dwell time and positioning. But it sounds like your approach is tackling one specific part, which would make for higher efficiency no matter what radiation source you used, or even if you did maybe a cryo approach.
Yep. So we have to replace the equations that we have with the new approach. So that those equations be solved every time that we update them.
And I just have one. I'm just going to ask one more question, and if anyone else has a question, please post it. But with regards to data that you need for doing your reinforced learning, it sounds like it's kind of a simulation. You're simulating data and feeding it back. And is there any source of real-time data that would be like a large data depository that might help you in your work and potentially in some type of AI training?
Yes, definitely. So for reinforcement learning, the initial point of planning, where we start, is very important. So the more access that we have to data, then we can make it run better. So the program feels better about the updates. At some point, we would like to train a neural network so it knows if it is a good plan that is generated or not. So I think that will help with a lot. We are in the process to ask for data. We have some couple, 2-3 set of data, but for a large amount of data from another institute, we have to do those kind of agreements so that they allow us to use it. But we are discussing it from institute to have access. So for now, everything is virtual. So like you said, we develop our own plans.
Right. Are there, of any other groups that are taking a neural net approach to any aspects of treatment planning for prostate?
They do, yeah. So AI is like very interesting field of research. So I have seen like in NIH panels and NIH projects that some of these are being practiced. So definitely on cancer, recognition is everywhere, right? Breast cancer, prostate cancer, based on imaging, that they want to know how suspicious the tissue is for cancer. But for planning, I have seen few institutes. So UCLA is very active in this field, in MRI ultrasound fusion, like procedures and everything. And some other institutes, yes. That's what I've seen.
Okay, great. All right, if there's no more questions, we'll just end it there. And I just want to mention again that our next talk is going to be on December 2nd, and it's Adam Yala. And Adam is doing fantastic work in breast cancer risk using AI models from many different institutions, over 1 million images in his models. So if you have time to look up some of his papers in the future, please do. Also, we're going to try to this is our first meeting, so it's kind of experimental. But I think that on future meetings, we're going to operate this more like an affinity group, to where we really want this to be like an interactive workshop where people can feel free to ask questions and we get to know each other to really advance the topics that we hear about. And so I think that this format of keeping the videos on and the everyone seeing each other is what we're going to stay with, instead of the more typical large workshop format where nobody sees who's in the room. And that's so that we can, over time, we'll get to know each other and each other's work. If you have speaker suggestions, please let us know. We'll also, probably on February 3rd, we're going to do a quick round robin type style. We'll invite in several people, including students, to present their work in a little bit quicker fashion. So maybe 5-minute talks, so that we can, hit a lot of topics and people can get to know each other's work fast. And we'll mix some of those in all the time with our featured speakers as well. So if you have any other thoughts or questions, please email me. I'm happy to get input. I thank Peter Washington, which helped us, organize all this. One last note is that all of our speakers will be receiving an AI PHI beer stein as part of their thank you for speaking, so that this makes it a little bit different than just being asked to to do a talk on Zoom again. You'll get this really wonderful beer stein, and we'll show you a picture of that next week, our next call. So thanks everyone. Look forward to seeing you on December 2nd. Bye-bye.